Hello. So in this section, we'll be looking at the ways we can sort of represent a vector. Right. So the first thing we're gonna look at and a recap from GCSE, and now these are column vectors. Right. We're gonna look at column vectors. So say for example, we had the vector A, and as a column, it's a 4, 1. Right. 4 then 1. Now, if we were to represent that vector then, say on a grid, right, XY axis, there we are, XY. Well, firstly, 4, the top number in the vector is the X part, so that's going to be 4, right, sort of like an X coordinate of 4, right, say that would be there, and then the next number 1, uh, sort of represents the Y coordinate, right, so that'd be, say, 1 there. So then obviously therefore that point is there, so then the vector would start from the origin and then connect to that point. uh, there we are, and so that vector would be vector A, right? So in general then, as a column vector, it's in the form xy, right, where it's sort of got the x coordinate on the top and the y coordinate on the bottom. Say for, as another example, we had the point B, which was -2, -5, say. So again, it'd be -2 on the x-axis, so say it'd be there. And then -5, so say it'd be down here somewhere. Then the point B would, the point would be there, right? That for that vector. So then if we join that point to the origin, well, then we get the vector B, right? This line, right, between the origin, which is like the starting point, and the point here, which is represented by the vector, the column vector, right? That line is the vector B, which is represented by the column, right? So that's as a recap, as a summary, how we can represent vectors using column notation in this way, right? Uh, I guess sort of the problem though is, obviously we know what it means, but it's not entirely formal, right? There's not really a precise sort of definition or expression of what this means as a vector, right? All we know is that the 4, for example, for A, the 4 represents the x part and the 1 represents the y part, but it's not really as it's in column form, but it's not actually technically properly as a vector, right? We can draw the vector, sure, but this isn't expressed particularly as a vector per se. Uh, but it just has a column of numbers, so it's not entirely clear, not entirely formal anyway, what this means, which is where we introduce something called ing. So let me take this example again. This A is 4, 1. So 4, 1. So we know what that means, right? As a column vector, obviously we just drew it. It's 4 on the x-axis and 1 on the y-axis, right? We just saw that. But then as a vector, then we can say this is 4i add 1j, right? And then I and j are vectors, which are underlined, right? Now, what does that mean then? Well, it means exactly the same thing. You can sort of think of I as the x part or the x component and j as the y part, right? So if we were to plot this then on an axis again, xy again, well, 4i, that's going to be 4 along the x-axis again, stay there, but it's going to be 4i now. And 1j, well, that'd be 1 on the y-axis, but it'd be 1j instead, okay? And so again, exact same idea. We then get the point there, and that's our vector A, right? Okay, so it's exactly the same thing, but now I basically and J are actual vectors, right? You can see that here. I've underlined it, so they represent vectors, and so I is like the x vector, and J is like the y vector, right? Pretty much. And if I take that example, then so that was that's the vector A. Well, the x component, right, is 4i, and the j component is 1j. Now 1j, just like with normal algebra, we can just call j, right? And so actually A could also be expressed as 4i and j, right? If I get rid of this 1 now. And so actually because I and j are technically two different vectors, right? I'm basically adding two vectors, right? Say I'm starting here, right? And I end here. Well, I'm going 4i along, I'm going to vector 4i along, and then up by a vector of j. Overall, I add them together. This is actually the triangle law, which we looked at last time. I'm adding two vectors together, right? And that's the idea, right? So I'm going, so the I component, right, the I vector represents how far on the x, how far along the x-axis we go, and then the j part is how far up the y-axis we go. So again, I is basically the x vector and j is the y vector, right? Right, as another example then, let's take this example B, right? So we said that B was -2, -5. So in IJ form, right, in this form here, it's going to be -2i -5j. And so if you were to draw that on a on this sort of grid, right, well, again, it'd be exactly the same as the last example. So -2 would be there on the x-axis, but it'd be -2i, and -5j would be there, so -5j. And so then we connect, that's our point, and then the vector would be the line between the point and the origin, right? And that'd be the vector B. But actually, it'd be the vector -2 -5j, right? Or -2i -5j. If I have enough room. There we are, okay? So that is basically all that means. So I and j then are the technical terms for vector, right? And so we can convert between the column form that we know from GCSE or wherever, the column form of the vector, we can then convert to sort of the more proper form of the vector, which is involving these I and j's, which essentially, hopefully you can spot the -2 is the x part, this is the x part, -2i, and then -5 is the y part of the vector, and -5j is the y part of that, okay? So I and j basically represent the x and y parts. So very simply, that's all we're dealing with. And more generally, you can express a column vector xy in the form xi add yj, okay? And that's all that means, okay? So then what we mean by I and j then more specifically, we can just say, because I represents, right, the x part, and then 1i would just be 1, 0, so 1 along the x-axis, right? And the j as a vector is 0, 1, as it like 1 unit on the y-axis, right? Because that's 1j, right? So that'd be 1 unit in the y-axis. So I and j basically are the vectors for x and y, essentially. Hopefully you can see. So as a very quick example then, let's have a look up here for the vector B. We saw that -2 -5 was -2i -5j. But then if we introduce these vectors for I and j as a column, that's going to be -2 lots of 1, 0, -5 lots of 0, 1. Then we can multiply it in the usual way. We can sort of multiply the columns as you see with GCSE. So we multiply the number -2 firstly by the top and the bottom numbers. So -2 times 1 is -2, and then -2 times 0 is 0, and then -5 times 0 is going to be 0. And then -5 times 1 will be -5, okay? And so then if we add these two vectors together, we get -2 -5. And there we are. We end up with the vector, that vector there, the column. So so I and j are exactly the same thing as column vectors, right? As you can see here. But so from now on, we will be basically primarily be working in this notation of i's and j's, right, to split it between sort of the x-axis and the y-axis. Okay, it's pretty standard to pretty similar to what we've already seen before from GCSE or wherever, but this is the more fancy or proper way of working with vectors, right, or writing down a vector, which we will be using from now on, and especially if you look at higher level maths, if you go to uni or do further maths, we will be I and J will pretty much be the standard, right? That's essentially what we'll be looking at then. So we're going to look at some examples then, right? So let's have a look at this example. We have A, which is 2, 6 as a column, and B, which is 3 minus 1. They're firstly asking us to find a third of A, right? Now, this works exactly the same way from GCSE when you're multiplying or adding vectors with numbers. They work how you expect. So if you do a third of A, that's the same as a third of the column 2, 6, right? And so that is essentially just times in both and the top and the bottom number by a third, right? So that would be 2 times a third and 6 times a third, and then 2 times a third is 2/3, and 6 times a third would be 2, right? And there we are. So that's a third of A as a column. Okay. Part B, and we could also write that in I and J notation. So that's 2/3 I add 2J. Okay, as in IJ form. There we are. Part B then is the vector A add the vector B. So again, that works how we expect. So the vector A is 2, 6. Add B, which would be the vector 3 minus 1. And so if we do that then, well, we do what we expect. We add the top numbers together, 2 and 3, and the bottom numbers together, 6 minus 1. If we do that computation, 2 over 3 is 5. 6 minus 1 is 5 as well. And again, we can also write that in I and J form to be 5I add 5J. Okay, so hopefully you start to get the idea of I and J now, how we write things down in that way. So literally I for like the top part or the X part, and J for the bottom or the Y part. Okay, part C, we need 2A minus 3B. So again, that's going to be 2 lots of the vector A, so the column 2, 6, minus 3 lots of the vector B, 3 minus 1. And so that worked how we expect. But firstly, we're going to, the 2 times 2 at 2, 6, we're going to multiply all numbers in the column by 2. So 2 times 2 is 4, 2 times 6 is 12, minus, then we're going to do 3 times the column. So that's 3 times 3, which is 9. 3 times minus 1 is minus 3. Then lastly, we need to subtract the vectors. So then we're going to subtract the top numbers. So 4 minus 9 is going to be minus 5. And 12 minus 3, that's a double negative, right? So we're adding it. So 12 add 3 be 15. And that is my vector. And again, in proper sort of vector form, we can say it's minus 5 lots of I, add 15 lots of J. Okay, there we are. Okay, now we look more into this I and J business. So they're asking us firstly to draw a diagram of the vector minus 3 lots of I, add J. Now again, this is basically 1 lots of J, right? There's a hidden 1, right? Just like with normal sort of algebra terms. But this is minus 3I and J. Well, it works in pretty much just how I said. Pretty much exactly the same as with normal column vectors or vectors, right? So the minus 3I, that's minus 3 on the x-axis. So it'd be minus 3, say here, but that'd be minus 3I. I'll do that down here. Minus 3 lots of I. Then J, that's 1, right? That's 1J, so that's 1 on the y-axis, but it'd be 1J. There we are. So then the point would be there. Okay. So from the origin, that's the vector. And this is the vector minus 3i add j. Okay. That's what that line represents. The vector there. Right, okay. Then it says for part B, write it as a column vector. So obviously we can go the other way as well. We can write as a vector minus 3i and j. Well, minus 3i, minus 3 is sort of the x part, so minus 3. And j, well, 1j, that would be 1. That's sort of the y part. And so that's that as a column vector there. Okay. Cool. Okay, let's have a look at this example then. We got A, the vector A, which is 3 lots of I minus 4j, and the vector B, which is 2I add 7j. Then it says for part A, find a half of A. So a half of A then, that's going to be a half then of this vector, 3I minus 4j, right? And exactly like with column vectors, we can split that up to, we can split that half up into each individual part. So we'd have to do 3 times a half firstly. So I'd say 3 times a half I add minus 4 times a half lots of j. And so then we can simplify it by 3 times a half firstly for the I part. That's going to be 3 over 2I. And then minus 4 times a half, that's going to be minus 2j. And that's it. Okay. So very, very similar to column vectors, right? Pretty much the same idea. We can, when we multiply by a number, say a half, we can times that by the two numbers in the two different components. So the I component and the j component. And we do it in the same way. Okay, part B. We need to find the vector A add B. It's a bit confusing. The question number is the same as the vector name. But hopefully you get what I'm saying. Okay, so the vector A add the vector B. So again, that's the vector 3i minus 4j. That's the vector A. And then the vector B is add 2i plus 7j. And so again, like with normal algebra, right? We can add the likewise terms together. So that all the I terms, 3i and 2j and 2i be 5i, and minus 4j plus 7j, well, minus 4 add 7 will be plus 3j, and there we are. Okay. Then part C, I'll do up here. We have 3 lots of A minus 2b. So again, that's going to be 3 lots of the vector A, which is 3i minus 4j, minus 2 lots of the vector B, which is 2i add 7j. And then again, like with column vectors or whatever, we multiply, each the vector term by term, right? So firstly, we're going to sort of expand this bracket, right? It's basically like I and j is basically just like normal algebra, right? So how we expand the bracket as we expect. So firstly, 3 times 3i, that's going to be 9i. Then 3 times minus 4j would be minus 12j. Then we're subtracting this, right? So then we expand the bracket 2, lots of 2i add 7j. But 2 times 2i would be would be 4i. So subtract 4i. And then minus 2 times 7j would be minus 14j. And then again, we can sort of collect the like terms, right? So we're going to have 9i minus 4i be 5i, right? And minus 12j minus 14j would be minus 26j. And there we are. Okay, cool. Okay, so again, the arithmetic with these vectors works in exactly how you expect, right? But yeah, let's have a look at this example. Given that A, the vector A is 2i add 5j, B is 12i minus 10j, And the vector C is minus 3i plus 9j. Find the vector A, add B, add C. So we're going to add all these three vectors together. And it also said using column vector notation. So that means we need to convert all these into columns, right? Into column vector form. So it needs to look like this, right? X, Y. So that's what we're going to do. So, okay, so we need to add the three vectors together, but as column vectors. So we need to convert the I and J stuff into our column form. Well, that's very easy. So 2i, that's just going to be 2 at the top, and then 5j be 5 there at the bottom. B, the vector B then, as a column, that'd be 12i, so 12 at the top, then minus 10j, so minus 10 at the bottom. Because again, the I and the j just means the x and the y part, right? But there we are. Then the vector C, minus 3i, that's minus 3 at the top, then 9j, 9 at the bottom. And there we are. So then if we're adding these three together, we can add them as columns, alternatively. So 2 and 5, add B, which is 12 minus 10, add C, which is minus 3, 9. So then we just add them in the usual way with columns. So add the top numbers together. So 2 add 12 minus 3, that'd be plus 11. Then 5 minus 10 add 9, that would be 4, right? And there we are. The question didn't specify to give my answer in this I and J form, but if you were to, you can then convert back to say that's 11i add 4j, right? But there we are. Cool. Right, okay, last example before we look at some exercises. We have the vector A, again, which is 5i and 2j, and the vector B, which is 3i minus 4j. We need to find the vector 2a minus b in terms of I and j. So that's telling me what my answer needs to be in, what form my answer needs to be in. We'll talk about that at the end. But first, we need to compute this, right? 2a minus b. So that's going to be 2 lots of a, the vector A, which is 5i. Plus 2j minus the vector B, so that's going to be minus 3i minus 4j there. So then we just need to sort of expand the brackets, right? So firstly, if we expand this bracket here, 2 lots of A, the vector A, so 2 lots of 5i add 2j. And 2 times 5i would be 10i, and 2 times 2j would be 4j. And then minus in this bracket, so we're going to get minus 3i, and then minus 4j would be plus 4j, as it's a double negative. And then we can just add the i's and the j's, right? So 10i minus 3i would be 7i, and 4j plus 4j would be 8j. And there we are. Now that's that answer in terms of I and j, right? That's what it means. We need to have our answer in this form. We could alternatively give it as a column vector. So that'd be then 7, 8. But the question did not say you can specify it in that. You have to put it in terms of I and j. So you have to pay attention to what the question wants, okay? But there we are. Okay, that's our final answer. Cool. Right, so hopefully you got a good flavour now for how working with I and j. Pretty much exactly the same as, you know, normal vectors that we've seen before. But yeah. Right, more questions then. So we have A, which is the vector A is P minus Q, the vector B, which is QP, and C, which is 7, 4. So we're going to mix a bit of algebra into it now, but again, it's the same idea. So we've given that the A at 2B equals the vector C. We need to find the values of P and Q. Well, that's what we're going to do. Let's just consider doing this then, computation. So A at 2B, if we were to do substitute our values of A and B in, that's telling me P minus Q for A, add 2 lots of B, which is QP, is going to get me C, which is 7, 4. And then, okay, we can actually simplify the left side, right? We can add these two vectors together. Well, firstly, we're going to have P minus Q, and then we can expand this, right? So 2 lots of P, Q, 2 lots of QP, obviously we times the top and the bottom by 2. We're going to then get add 2Q, 2P, and that's going to equal 7, 4. And then we can add the two vectors together, right? So then if we do that, say over here, we are going to get P add 2Q, that'd be P add 2Q, minus Q add 2P is going to equal 7, 4, right? And so these two vectors then, the top part, because they're equal to each other, the two vectors, the top part has to equal the bottom part, right? So therefore, P add 2Q has to equal 7, and minus Q add 2P has to equal 4, right? And so actually, you can spot these as simultaneous equations, right? Now, we label that equation 1 and 2. Well, I notice I have, no, what do I notice? Well, then I can solve them, right? So there are many ways you can solve this simultaneous equation. We looked at simultaneous equations in chapter 3, but I guess we could use elimination, right? So let's match the p, right? The 2p and the p here. Let's make the p's the same, right? So I have p on equation 1, so I can double equation 1 to get 2p. And so I can cancel that out. If I then double equation 1, I then get 2p add 4q equals 14. And so if I then bring back equation 2, so minus q add 2p. So I'm going to rewrite that as 2p minus q equals 4. Then I can subtract both equations, right? If I subtract that, so 2p minus 2p is 0. 4q minus q, then that's a double negative. So 4q add q be 5q. And then 14 minus 4 is 10. So 5q equals 10. Therefore q, if I divide by 5, is 2. Okay, so if I found q is 2, so then I can substitute that into either equation, right, to get p. I'm going to substitute that into equation 1. So I'm going to do it up here. Sub q equals 2 into equation 1. And so therefore p add 2q, so I'm using this one, right? P add 2q, that's going to be 2 lots of 2 equals 7. And so therefore p add 4, which is what that simplifies to, p add 4 equals 7. Therefore p is going to equal 3. And there we are. Those are my values for q and p. Okay, cool. There we are. And so again, got simultaneous equations is here. So again, with the A level, do not forget that loads of different topics can link together in questions. So make sure you don't avoid any topics in your revision or your learning. Because questions might involve bringing multiple topics together, like in this case here. But hopefully that made sense. But yeah, let's have a look at this next question. Question 10. Right, we are told that the resultant of the vectors A, the vector A, which is 3i minus 2j, and the vector B, which is pi minus 2pj, is parallel to the vector C, which is 2i minus 3j. So there's a lot of stuff going on. So we need to find the value. We need to find the value of p and the resultant of vectors A and B. So firstly, the resultant of vectors A and B, right? What does that actually mean? So the resultant is basically adding the two together, right? That's what that means. So resultant of A and B. We will see a bit more of that later on in the course but for now, the resultant of two vectors A and B is adding them together. Okay. But if we add them together, then A and B, we're going to get 3i minus 2j for A. Add B, which is going to be pi minus 2pj. Right. So if we do that, then, well, if we add the I terms, we're going to get 3 add p lots of I. Add minus 2 minus 2p lots of j. Now actually, as a column then, we can say that's going to be 3 add p on the top, and the bottom number with minus 2 minus 2p. And there we are. So that's the resultant of vectors A and B. We just add them together. Now we are told it's parallel to this other vector C. Now remember last time we discussed that parallel vectors, two vectors say R and T, they're parallel. The two vectors are parallel if they're multiples of each other. So we can say one vector R is a multiple of another vector T, right? So two vectors are parallel, they're multiples of each other, right? That means then if this resultant vector that I just found is parallel to the vector C, then this resultant is a multiple of the vector C. Now actually a C then, we can write this in column form as well, to then 2 minus 3, okay? So then these two vectors then, the resultant vector here and the vector C, they're parallel, so they have to be multiples of each other. We can write that then as to say that this vector is going to be a multiple or multiple K, say, lots of the vector C 2 minus 3. Right? Hopefully you see what I did there then. So from there, I can, I don't have much room again. I'll do it down here. I'll continue on. So then we can sort of expand the bracket then. So 3 add P minus 2 minus 2P is going to equal, if I expand this bracket, right? So if I multiply K by sort of the vector, the column, right? So K times 2 be 2K. K times minus 3 be minus 3K. There, right? So then directly you can see the top number has to equal the bottom. The top numbers have to equal and the bottom numbers have to equal 2. That means then that therefore P add 3 has to equal 2K, and also minus 2P minus 2 has to equal minus 3K. And again then we've got simultaneous equations. So this time I'm going to spice it up, and now I'm going to use substitution instead to solve these two equations, right? If I call them equation 1 and 2. So again, simultaneous equations, right? Two equations with two unknowns. I'm going to rearrange for P. I think that's the smartest, safest way to do it. So therefore I'm going to rearrange the top one to then say that P is going to be 2K minus 3, right? So then I'm going to sub that into the other equation. So sub P into the other equation 2. Then I'm going to get minus 2P, that's going to be minus 2 lots of 2K minus 3, right? That's what P is there. Minus 2 is equal to minus 3K, right? That's just equation 2 right there. So then I could just solve for K, right? So if I expand the bracket, well, minus 2 times 2K would be minus 4K. Minus 2 times minus 3 would be plus 6. Minus 2 is minus 3K. Then I can add the 4K to both sides. So then I get K, 6 minus 2, which is 4. Cool. So that's K then, but then to find P, well, I know P is 2K minus 3. So therefore P is 2 lots of 4 minus 3. And so P then is going to be 2 times 4, which is 8, minus 3 is 5. And that is my value for P there. So there we are. So that's part A. Then the value of P, which is 5. I'll do that here. P is 5. And then for part B then, it says find the resultant of vectors A and B. Now we already did that in part A. This was the resultant vector, right? 3 add P minus 2 minus 2P, right? But now we know what P is, so we can substitute it in to get the actual, the numerical vector, right? The actual physical number for P. Right, so if I substitute P in then, this becomes 3 add 5. And then minus 2 lots of 5. Which would get me... I don't have much room. Well, 3 add 5 would be 8, right? And then minus 2 lots of 5, that's going to be minus 2 minus 10. So that's going to be minus 12, right? And there we are. 8 minus 12 is the resultant vector there. Okay? I'll make a note of that. Cool. So there we are. Right. Okay. Okay, we've got this final question. I'm going to get rid of this now to not this working out to not distract from this question. But this question says we're given OABC is a parallelogram, and we're given P divides AC in the ratio 3 to 2. OA is 2i add 4j, and OC is 7i. Find these three vectors, right? Essentially. So if I get rid of this now. Okay, so let's go back to this question then. We first need to find AC. But firstly, I've got some information, right? I am told OA, which is this vector there, is 2i add 4j. So if I add that in. There we are. And OC is 7i, right? There we are. We're also given that P divides AC in the ratio 3 to 2. So that means then that the first part from A to P is going to be three, right? Is going to be three parts, right? And that means the other part of the line of P to C is going to be the remaining two parts. But overall, then we can say that A to P is going to be 3/5 of the total AC, right? And then we can also say that then P to C is also going to be the remaining 2/5, right? Remember, I'm considering the whole total, right? If the whole line AC is the whole part, right? Now that's 5 parts, right? So it's going to be 3/5, right, of the line AC. So if I, there we are. Now the first question then is to find AC, right? So it's going to be that vector, right? The diagonal. Right, okay. So again, the whole objective is we're going to start at A and we need to end at C. So what path can we take? Obviously, we can't go directly from A to C because we don't know the vector. But actually, we can go from A to O and then O to C, right? And then we end up at C. So then we can go along the vector AO, add O to C, right? And there we are. But actually, O to A is this vector, but we want to go the other way. So it's going to be the negative of the vector. So OA, we want to do the negative of that, right? If we want to go from OAO instead. And then O to C, well, O to C is 7i, right? But then minus OA, well, OA is this 2i add 4j, right? So it's going to be minus 2i plus 4j plus 7i. So then if we sort of expand this bracket then, we're going to get minus 2i minus 4j plus 7i. So then minus 2i minus 2i add 7i, that'd be plus 5i. And then minus 4j. And there we are. So that's the vector AC. And it's said to give in IJ format, which is what we did, and as a column vector. So very simply then, as a column vector, we can also say that's going to be 5 minus 4 there. Cool. Part B, we need to find the vector O to P. So that's going to be starting now at O there and then at P. Well, how are we gonna get from O to P? Well, I could go from O to A and then A to P, right? Because I found AC now, right? So I know stuff about that line A to P. Well, so O to P then is going to be O to A, add A to P, right? Okay. Well, O to A is again just this vector 2i, add 4j, and then A to P. Well, as we just discussed up here, A to P, well, because P divides AC in the form 3 to 2, that basically means the ratio A to P to then P to C, right? So the line from A to P and then the line from P to C, that's going to be 3 to 2, right? That's the same ratio, 3 to 2. But the whole line, of course, is just AC. So in total, AC would equal 5, right? Well, then that means A to P, which is 3 parts, is going to be 3/5 of AC, right? Hence what we've got up here. A to P is 3/5 of AC, 3/5 of AC, right? So then we can say that's going to be a 3/5 of AC for AP there, okay? Hopefully it made sense. I'm just using the ratio they've given us there. Okay. But I already worked out AC, right? In the first part, it's 5i minus 4j. So then I can say 2i add 4j, then 3/5 of AC, which is 5i minus 4j. And so then if I do 2i add 4j, then if I sort of expand this bracket, right? Well, 3/5 times 5i, that'd be 3i. So add 3i. And then 3/5 times minus 4j, that would be minus 12 over 5j. Okay. So then we can just add the I and the j's, right? As usual. Well, then 2i plus 3i would be 5i. And then 4j minus 12/5 j would get me 8 plus 8/5 of j. And there we are. There we are. Cool. And then as a column vector, then that just would be simply 5 and then 8/5. And there we are. Right, then part C then it says A to P. Well, that's interesting. We already worked that out. I think the question meant to find AP for part B and then O to P, because we already found AP in part B. So A to P then, as we worked out, A to P, as we just discussed up here, is 3/5 of AC, which we already just worked out, to be honest. But I'll do it again. So it's going to be 3/5 of AC, which we worked out in part A. So it's going to be 5i minus 4j. So it's going to be 3/5 times 5, that'd be 3i. And then minus 4j, that would be 3/5 times minus 4, which again would be minus 12/5 j. So again, 3/5 times minus 4j gets me that. So then as a column form, that'd be 3 minus 12/5. And there's my answer. Cool. So those are all the questions then. So again, hopefully you become a bit familiar with I and J now. Exactly the same way as with normal vectors, with column vectors. They mean the same thing again. I is just the X component and the Y, and the J is the Y component. And then we add them in the same way, okay? But in the way, and we add and multiply them in the way we expect, right? But yeah, this question's a bit funny. I think it's meant to say part B find AP and then part C find OP. Because to find OP we needed to find AP. I think the textbook was a bit weird there. But either way, we've got the answer. So yeah, so that is I and J notation. So I'm gonna leave it there, but I'll see you next time.